Bluetooth Low Energy. Bluetooth Low Energy Bluetooth Low, colloquially BLE, formerly marketed as Bluetooth Smart, is a wireless personal area network technology designed and marketed by the Bluetooth Special Interest Group Bluetooth SIG, aimed at novel applications in the healthcare, fitness, beacons, security, and home entertainment industries. It is independent of classic Bluetooth and has no compatibility, but BR/EDR and LoW can coexist. The original specification was developed by Nokia in 2006 under the name Wibree, which was integrated into Bluetooth 4.0 in December 2009 as Bluetooth Low Energy. Compared to classic Bluetooth, Bluetooth Low Energy is intended to provide considerably reduced power consumption and cost while maintaining a similar communication range. Mobile operating systems including iOS, Android, Windows Phone and BlackBerry, as well as macOS, Linux, Windows 8 and Windows 10, natively support Bluetooth Low Energy. Compatibility. Bluetooth Low Energy is distinct from the previous, often called classic Bluetooth Basic Rate/Enhanced Data Rate BR/EDR protocol, but the two protocols can both be supported by one device. The Bluetooth 4.0 specification permits devices to implement either or both of the LoW and BR/EDR systems. Bluetooth Low Energy uses the same 2.4 GHz radio frequencies as classic Bluetooth, which allows dual-mode devices to share a single radio antenna, but uses a simpler modulation system. Branding. In 2011, the Bluetooth SIG announced the Bluetooth Smart logo so as to clarify compatibility between the new low-energy devices and other Bluetooth devices. Bluetooth Smart Ready indicates a dual-mode device compatible with both classic and low-energy peripherals. Bluetooth Smart indicates a low-energy only device which requires either a Smart Ready or another smart device in order to function. With the May 2016 Bluetooth SIG branding information, the Bluetooth SIG began phasing out the Bluetooth Smart and Bluetooth Smart Ready logos and word marks and reverted to using the Bluetooth logo and word mark in a new blue color. Target market. The Bluetooth SIG identifies a number of markets for low-energy technology, particularly in the smart home, health, sport, and fitness sectors. Cited advantages include low power requirements operating for months or years on a button cell, small size and low cost, compatibility with a large installed base of mobile phones, tablets, and computers. History. In 2001, researchers at Nokia determined various scenarios that contemporary wireless technologies did not address. The company began developing a wireless technology adapted from the Bluetooth standard, which would provide lower power usage and cost while minimizing its differences from Bluetooth technology. The results were published in 2004 using the name Bluetooth Low End extension. After further development with partners, in particular Logitech, and within the European project Mimosa, and actively promoted and supported by STMicroelectronics since its early stage, the technology was released to the public in October 2006 with the brand name Wibree. After negotiations with Bluetooth SIG members, an agreement was reached in June 2007 to include Wibree in a future Bluetooth specification as a Bluetooth ultra-low power technology. The technology was marketed as Bluetooth Smart, and integration into version 4.0 of the core specification was completed in early 2010. The first smartphone to implement the 4.0 specification was the iPhone 4S, released in October 2011. A number of other manufacturers released Bluetooth Low Energy ready devices in 2012. The Bluetooth SIG officially unveiled Bluetooth 5 on 16 June 2016 during a media event in London. One change on the marketing side is that the point number was dropped, so it is now just called Bluetooth 5 and not Bluetooth 5.0 or 5.0 like for Bluetooth 4.0. This decision was made to simplify marketing and communicate user benefits more effectively. On the technical side, Bluetooth 5 will quadruple the range by using increased transmit power or coded physical layer, double the speed by using optional half of the symbol time compared to Bluetooth 4x, and provide an 8-fold increase in data broadcasting capacity by increasing the advertising data length of low-energy Bluetooth transmissions compared. An advertising packet in Bluetooth parlance is the information that is exchanged between two devices before pairing, i.e., when they are not connected. For example, advertising packets is what lets you see the name of a Bluetooth device before you can pair it. Bluetooth 5 will increase the data length of this advertising packet. The length of this packet in Bluetooth 4x was 31 bytes for broadcast topology. The Bluetooth SIG released mesh profile and mesh model specifications officially on 18 July 2017. Mesh specification enables using Bluetooth Low Energy for many-to-many device communications for home automation, sensor networks, and other applications. Applications. Borrowing from the original Bluetooth specification, the Bluetooth SIG defines several profiles specifications for how a device works in a particular application for low-energy devices. Manufacturers are expected to implement the appropriate specifications for their device in order to ensure compatibility. A device may contain implementations of multiple profiles. The majority of current low-energy application profiles are based on the generic attribute profile GATT, a general specification for sending and receiving short pieces of data, known as attributes, over a low-energy link. The Bluetooth mesh profile is an exception to this rule, being based on the general access profile GAP. Mesh profiles. Bluetooth mesh profiles use Bluetooth Low Energy to communicate with other Bluetooth Low Energy devices in the network. Each device can pass the information forward to other Bluetooth Low Energy devices, creating a mesh effect. For example, switching off an entire building of lights from a single smartphone. Mesh profile for base mesh networking. MMDL mesh models for application layer definitions. Term model is used in mesh specifications instead of profile. Healthcare profiles. There are many profiles for Bluetooth Low Energy devices in healthcare applications. The Continua Health Alliance Consortium promotes these in cooperation with the Bluetooth SIG. VLP blood pressure profile for blood pressure measurement. HTP health thermometer profile for medical temperature measurement devices. GLP glucose profile for blood glucose monitors. CGMP continuous glucose monitor profile. Sports and fitness profiles. Profiles for sporting and fitness accessories include the CS Body Composition Service, CSCP cycling speed and cadence profile for sensors attached to a bicycle or exercise bike to measure cadence and wheel speed. CPP cycling power profile, HRP heart rate profile for devices which measure heart rate, LNP location and navigation profile, RSCP running speed and cadence profile, WSP weight scale profile, Internet connectivity, IPSP Internet Protocol Support Profile, Generic Sensors, ESP Environmental Sensing Profile, UDS User Data Service, HID Connectivity, HOP HID over GATT Profile allowing Bluetooth-enabled wireless mice, keyboards, and other devices offering long-lasting battery life. Proximity Sensing. Electronic leash applications are well suited to the long battery life possible for always-on devices. Manufacturers of iBeacon devices implement the appropriate specifications for their device to make use of proximity sensing capabilities supported by Apple's iOS devices. Relevant application profiles include FMP. The Find Me profile allows one device to issue an alert on a second misplaced device. PXP. The proximity profile allows a proximity monitor to detect whether a proximity reporter is within a close range. Physical proximity can be estimated using the radio receiver's RSSI value, although this does not have absolute calibration of distances. Typically, an alarm may be sounded when the distance between the devices exceeds a set threshold. Alerts and time profiles. The phone alert status profile and alert notification profile allow a client device to receive notifications such as incoming call alerts from another device. The time profile allows current time and time zone information on a client device to be set from a server device, such as between a wristwatch and a mobile phone's network time. Battery. The battery service exposes the battery state and battery level of a single battery or set of batteries in a device. Audio. Announced in January 2020, the audio will allow the protocol to carry sound and add features such as one set of headphones connecting to multiple audio sources or multiple headphones connecting to one source. It will also add support for hearing aids. Compared with standard Bluetooth audio, it will offer longer battery life. Contact tracing and notification. In December 2020, the Bluetooth SIG released a draft specification for a wearable exposure notification service. This service will allow exposure notification services on wearable devices to communicate with implementation chip. Starting in late 2009, Bluetooth low-energy integrated circuits were announced by a number of manufacturers. These IC commonly used software radios, so updates to the specification can be accommodated through a firmware upgrade. Hardware. Current mobile devices are commonly released with hardware and software support for both classic Bluetooth and Bluetooth Low Energy. Operating systems. iOS 5 and later. Windows Phone 8.1. Windows 8 and later Windows 7 requires drivers from Bluetooth radio manufacturer supporting BLE, as it has no built-in generic BLE drivers. Android 4.3 and later. BlackBerry 10. Linux 3.4 and later through BlueZ 5.0. Unison OS 5.2, macOS 10.10. Technical details. Radio interface. Bluetooth Low Energy technology operates in the same spectrum range, the 2.400 2.4835 GHz ISM band as classic Bluetooth technology, but uses a different set of channels. Instead of the classic Bluetooth 79 1 MHz channels, Bluetooth Low Energy has 42 MHz channels. Within a channel, data is transmitted using Gaussian frequency shift modulation, similar to classic Bluetooth's basic rate scheme. The bit rate is 1 Mbit/s with an option of 2 Mbit/s in Bluetooth 5, and the maximum transmit power is 10 MW 100 MW in Bluetooth 5. Further details are given in Volume 6, Part A Physical Layer Specification of the Bluetooth Core Specification v4.0. Bluetooth Low Energy uses frequency hopping to counteract narrowband interference problems. Classic Bluetooth also uses frequency hopping, but the details are different. As a result, while both FCC and ETSI classify Bluetooth technology as an FHSS scheme, Bluetooth Low Energy is classified as a system using digital modulation techniques or a direct sequence spread spectrum. More technical details may be obtained from official specification as published by the Bluetooth SIG. Note that power consumption is not part of the Bluetooth specification. Advertising and discovery. BLE devices are detected through a procedure based on broadcasting advertising packets. This is done using 3 separate channels frequencies in order to reduce interference. The advertising device sends a packet on at least one of these 3 channels, with a repetition period called the advertising interval. For reducing the chance of multiple consecutive collisions, a random delay of up to 10 milliseconds is added to each advertising interval. The scanner listens to the channel for a duration called the scan window, which is periodically repeated every scan interval. The discovery latency is therefore determined by a probabilistic process and depends on the 3 parameters, viz., the advertising interval, the scan interval, and the scan window. The discovery scheme of BLE adopts a periodic interval-based technique, for which upper bounds on the discovery latency can be inferred from most parametrizations. While the discovery latencies of BLE can be approximated by models for purely periodic interval-based protocols, the random delay added to each advertising interval and the three-channel discovery can cause deviations from these predictions, or potentially lead to unbounded latencies for certain parameterizations. Security. Software model. All Bluetooth low-energy devices use the generic attribute profile GATT. The application programming interface offered by a Bluetooth low-energy aware operating system will typically be based around GATT concepts. It has the following terminology. Client, a device that initiates GET commands and requests and accepts responses, for example, a computer or smartphone. Server, ver, a device that receives GET commands and requests and returns responses, for example, a temperature sensor. Characteristic, a data value transferred between client and server, for example, the current battery voltage. Service, a collection of related characteristics which operate together to perform a particular function. For instance, the health thermometer service includes characteristics for a temperature measurement value and a time interval between measurements. Descriptor. A descriptor provides additional information about a characteristic. For instance, a temperature value characteristic may have an indication of its units, e.g. Celsius, and the maximum and minimum values which the sensor can measure. Descriptors are optional. Each characteristic can have any number of descriptors. Some service and characteristic values are used for administrative purposes. For instance, the model name and serial number can be read as standard characteristics within the generic access service. Services may also include other services as subfunctions. The main functions of the device are so-called primary services, and the auxiliary functions they refer to are secondary services. Identifiers, services, characteristics, and descriptors are collectively referred to as attributes and identified by AUIDs. Any implementer may pick a random or pseudo-random AUID for proprietary uses, but the Bluetooth SIG have reserved a range of AUIDs of the form XXXXXXXXX-1000-8000-805 F9B34 FB for standard attribute. For efficiency, these identifiers are represented as 16-bit or 32-bit values in the protocol, rather than the 128 bits required for a full AUID. For example, the device information service has the shortcode 0x180A rather than 180 as 1000. ZIND. O. The full list is kept in the Bluetooth assigned numbers document online. GET operations. The GATT protocol provides a number of commands for the client to discover information about the server. These include: discover AUIDs for all primary services, find a service with a given AUID, find secondary services for a given primary service, discover all characteristics for a given service, find characteristics matching a given AUID, read all descriptors for a particular characteristic. Commands are also provided to read data transfer from server to client and write from client. A value may be read either by specifying the characteristics of AUID or by a handle value which is returned by the information discovery commands above. Write operations always identify the characteristic by handle, but have a choice of whether or not a response from the server is required. Long read and long write operations can be used when the length of the characteristics data exceeds the MTU of the radial link. Finally, GET offers notifications and indications. The client may request a notification for a particular characteristic from the server. The server can then send the value to the client whenever it becomes available. For instance, a temperature sensor server may notify its client every time it takes a measurement. This avoids the need for the client to poll the server, which would require the server's radio circuitry. An indication is similar to a notification, except that it requires a response from the client as confirmation that it has received the message. Battery impact. Bluetooth Low Energy is designed to enable devices to have very low power consumption. Several chip makers, including Cambridge Silicon Radio, Dialog Semiconductor, Nordic Semiconductor, ST Microelectronics, Cypress Semiconductor, Silicon Labs, and Texas Instruments, had introduced Bluetooth Low Energy optimized chipsets by 2014. Devices with peripheral and central roles have different power requirements. A study by beacon software company Ace Labs reported that peripherals, such as proximity beacons, usually function for 1–2 years powered by a 1000 mAh coin cell battery. This is possible because of the power efficiency of Bluetooth Low Energy protocol, which only transmits small packets as compared to Bluetooth Classic, which is also suitable for audio and high bandwidth data. In contrast, a continuous scan for the same beacons in central role can consume 1000 mAh in a few hours. Android and iOS devices also have very different battery impact depending on type of scans and the number of Bluetooth Low Energy devices in the vicinity. With newer chipsets and advances in software, by 2014 both Android and iOS phones had negligible power consumption in real-life Bluetooth Low Energy use. 2M5 Bluetooth 5 has introduced a new transmission mode with a doubled symbol rate. Bluetooth LE has been traditionally transmitting 1 bit per symbol, so that theoretically the data rate doubles as well. However, the new mode doubles the bandwidth from about 1 MHz to about 2 MHz, which makes for more interferences on the edge regions. The partitioning of the ISM frequency band has not changed, being still 40 channels, spaced at a distance of 2 MHz. This is an essential difference over Bluetooth 2 EDR, which did also double the data rate, but it is doing that by employing a P/4 DQPSK or 8 DPSK phase modulation on a 1 MHz chip. The traditional transmission of 1 Mbit in the Bluetooth basic rate was renamed 1 mphy in Bluetooth 5. The new mode at a doubled symbol speed was introduced as the 2 mphy. In Bluetooth Low Energy, every transmission starts on the 1 mphy, leaving it to the application to initiate a switch to the 2 mphy. In that case, both sender and receiver will switch to the 2 mphy for transmissions. This is designed to facilitate firmware updates, where the application can switch back to a traditional 1 mphy in case of errors. In reality, the target device should be close to the programming station at a few meters. Low-coded, moded. Bluetooth 5 has introduced 2 new modes with lower data rate. The symbol rate of the new coded PHY is the same as the base rate, 1 mphy, but in mode S=2 there are 2 symbols transmitted per data bit. In mode S=2 only a simple pattern mapping P=1 is used, which simply produces the same stuffing bit for each input data bit. In mode S=8 there are 8 symbols per data bit, with a pattern mapping P=4 producing contrasting symbol sequences. A 0 bit is encoded as binary 11 and a 1 bit is encoded as binary 1100. In mode S=2 using P=1 the range doubles approximately, while in mode S=8 using P=4 it does quadruple. The low-coded transmissions have not only changed the error correction scheme, but it uses a fundamentally new packet format. Each low-coded burst consists of 3 blocks. The switch block extended preamble is transmitted on the LA1 mphy, but it only consists of 10 times a binary 111,100 pattern. These 80 bits are not FEC encoded as usual, but they are sent directly to the radio channel. It is followed by a header block FEC block 1, which is always transmitted in S=8 mode. The header block only contains the destination address, access address /32-bit, and an encoding flag coding indicator /2-bit. The coding indicator defines the pattern mapping used for the following payload block FEC block 2, where S=2 is possible. The new packet format of Bluetooth 5 allows transmitting from 2 up to 256 bytes as the payload in a single burst. This is a lot more than the maximum of 31 bytes in Bluetooth 4. Along with reach measurements, this should allow for localization functions. As a whole, the quadrupled range at the same transmission power is achieved at the expense of a lower data being at an eighth with 125 kbit. The old transmission packet format, as it continues to be used in the 1 mphy and 2 mphy modes, has been named uncoded in Bluetooth. 5. The intermediate low-coded S equals 2 mode allows for a 500 kbit data rate in the payload, which is both beneficial for shorter latencies as well lower power consumption as the burst time itself is shorter.